Hi, it's my pleasure today to introduce Laís, who was our intern this summer. And by way of introduction, I just want to share two things that I really appreciated about her participation in our group this summer. One is her sharing of these delicious little chocolate balls that she tells us are traditional birthday party food for kids in Brazil. But there were no kids at our group meeting, and we all enjoyed them greatly. So I appreciated that cultural exchange. And the second thing is, I learned partway through the summer that Laís, she's going to talk to you about some modeling work that she did this summer today, but I learned partway through the summer that she thought she was coming to do a project that was entirely modeling. It was actually a project that was about half modeling and half field work. And I really appreciated the way she stepped up and did the field work and was a great contributor, despite the fact that our cornfields had bugs and birds and all kinds of creepy things. So thanks, Laís.
Thank you. So my project title is The Effects of Agricultural Management Practices on Nitrogen Inputs to Great Rivers. As you may know, nitrogen is one of the elements that is the most abundant in the environment, but is also the one that is the least available to most organisms because it's mostly in its molecular form, that is the non-reactive nitrogen. The reactive nitrogen is the nitrogen in all of the other forms as we know, like nitrous oxide or ammonia or nitrate, etc. This reactive nitrogen, even though it's necessary to sustain life, and it's important to plants and humans and animals, in excess, it's related to several environmental problems, even in human health, like respiratory problems or cancer and etc. But our major concern here is the effects in aquatic systems. Because when this reactive nitrogen reaches streams and lakes and rivers, it's related to problems such as acidification, eutrophication, loss of biodiversity, habitat degradation, hypoxia, etc. So in agricultural systems, this is a concern as well because of use of fertilizers. As we know, there is nitrogen in fertilizer, and approximately half of this nitrogen is incorporated by crops, but the other half is lost to the atmosphere as nitrous oxide or to aquatic systems, mostly as nitrate. So it's necessary to properly manage these nitrogen losses, and to do that, we can use mathematical models to help us predict it. So the objective of this project is to analyze nitrous oxide emissions and nitrate leaching in agricultural systems using the Denitrification-Decomposition model, the DNDC, and to determine controlling factors in the model's predictions. So DNDC is a computer model that predicts nitrogen outputs from agricultural ecosystems, and it basically consists of two models. The first one is driven by ecological factors, such as climate, vegetation, anthropogenic activity, activities such as the use of fertilizer and the amount of fertilizer, or the tillage method, or if it was irrigated or not, and all of these activities done by the farmers. And soil environmental variables like pH, clay fraction, etc. So all of this information is input to the model and then have several different outputs. But what is interesting for us is the nitrous oxide and the nitrate. The nitrate for all of the other reasons I said in the previous slide, but nitrous oxide specifically because once this nitrogen is in the environment, it's easily transferable to other systems, because it can cause acidity in precipitation, and then precipitates and goes back to the soil, and then from the soil it can reach aquatic system as well. And the DNDC was developed by Dr. Lee, and that's where we adapted this image. So how we did that? So we ran DNDC with literature parameters from 2 sites in Iowa, and the first one was from Parkin and Kaspar, and we used that to use the nitrous oxide data, and we used other paper from Kaspar, also from the same author, to use the nitrate data. And at the same time, we were sampling the field to connect these two parameters. So we've been sampling throughout these 8 weeks or 9 weeks, but fortunately, our data was too preliminary to have statistical analysis, and that's why we're not going to talk about this in this presentation. So to better analyze this, the model's performance, we modeled different scenarios, such as different tillage methods, the use of cover crops or not, and fertilizer applications. So those are our main results. In this first graph, we're analyzing nitrous oxide fluxes, and in the y-axis, we have the flux of N2O. In the x-axis, we have the years. But now we're looking at the fertilizer application. In this graph, the odd years, we had a rotation of corn and soybean. So in the odd years, we have corn plantation, and in even years, we had soybean. And we use fertilizers in corn plantations, but not in soybean. So we can clearly see the difference of peaks in years with corn and years that soybean was planted because of the fertilizer. So we could see the relation of fertilizer in nitrous oxide emissions. So now we're still looking at the same graph, but now we're looking at the tillage method. So in this side, we had areas with no-till and area where chisel plow was used. And we can clearly see they started using this method from 2002 on. So we can clearly see the difference of peak of emissions of nitrous oxide when you use that tillage method. Even though literature typically shows that there is no difference in nitrous oxide emissions, but we didn't have time to troubleshoot why the model had this prediction. So we don't know if there was a model fault or if there's something wrong, if there's something different in the site. In this graph, we're now using the second paper, and we're analyzing nitrate leaching. And for this graph, we're looking at the use of cover crop. So in the y-axis, we have the nitrate leaching, and in the x-axis, we have the years. The blue line here is the site where there was a rye as cover crop, and the orange line is the site there was no cover crop. So we can clearly see that where we used rye as a cover crop, there was the amount of nitrate was reduced. So we also compared the nitrate leaching with meteorological data. So in this first one, we're looking at temperature. So this is for a specific year, and in the x-axis we have the days of the year, and the first y-axis we have the nitrate leaching, and the second y-axis we have temperature. So the blue line in this graph is the temperature, and the black line is the predictions from DNDC. So you could also clearly see a relation between the temperature and the predictions of nitrate, because days where we had extremely low temperature, we had predictions of 0 nitrate leaching. In those days, the 0 is around here, 0 Celsius. And we can see that when it went to 0 or below 0, our predictions always also went to 0. And when it had like rapid decreases of temperature, like in these specific days, the predictions of nitrate also decreased. Then we compared with temperature, with precipitation, sorry. So it's the same graph, it's for the same year, but now the red line is precipitation values in centimeters. And we can also see how some peaks of precipitation matches with peaks of predictions of nitrate. This happens several times, but of course some other factors affect these predictions. So we also point out the days that we had fertilizer application for that year. They applied fertilizer in 2 days, and then we can clearly see the peaks of nitrate leaching for that days. So you could conclude that the DNDC results showed lower flux of nitrous oxide in sites with no-till than sites with chisel plow, and that the rye cover crop in the studded site decreased the nitrate leaching, and also that fertilization meteorological data, such as precipitation, temperature, are controlling factors for nitrous oxide predictions in DNDC, as is broadly known and published in literature. So thank you to the National Great Rivers Research and Education Center. Thanks to Illinois American Water for funding this project, to Lewis and Clark Community College. Thanks to Dr. Zilles, to Mary Foltz, and to Dr. Sotiria that contributed to this project. Those are the complete references that we used. And if you have any questions.
Questions?
Nice job on your presentation. Out of those factors that influence the nitrate leaching, which ones had the strongest influence on the variance?
Those graphs was just for 1 year for one crop, but we had several of them, and could clearly see that temperature was one of the factors that influenced the most.
Oh, okay, thank you.
Thank you.
We've got some time, so any more questions for Laís?
So, hi, Laís. I was wondering, what is the physical cause of the correlation between low temperatures and low nitrate leaching?
I'm afraid I wouldn't know how to answer that because we didn't have much time to make this relation, but we saw in papers, published papers, that this relation exists. It was kind of expected, but I'm afraid I wouldn't know how to tell you why.
Okay, thank you.
Mm-hmm.
Hey, Lais. Is there a spatial component to this modeling? I mean, is it, there wasn't any sort of, so the input, it's, I mean, there's no like GIS input to it or like
Actually, yes, DNDC, there is two methods of running, and there is the region mode and the site mode. The site mode was input all those parameters that I showed in the methods, like soil parameters and climate parameters. Some of them were available in the papers, some others we had to look into online databases. But there's also the region mode where you can input GIS files, but that was not the case for us. That's not how we ran the model.
Okay.
We have time for one more if there's any out there. Okay then, thank you very much.